Hello students, welcome to Abdemi's YouTube platform. Today we will consider two typical MCQs from thermodynamics. See the statement of the problem. First case, first one. Two identical containers A and B with frictionless pistons contain the same ideal gas at the same temperature and the same volume V. The mass of the gas in A is Ma and that in B is Mb. The gas in each cylinder is now allowed to expand isothermally to the same final volume 2V. The change in the pressure in A and B are found to be delta P and 1.5 delta P respectively. Then which one of the four options A, B, C, D is correct, that is to be found out. So two identical containers A and B fitted with frictionless pistons. So consider one container, there is a piston, there is another container, identical container. This is container A, this is container B. Having the same ideal gas at same temperature is same for both the gas and volume is also same for both the containers. Now the mass of the gas in A is Ma and that in B is Mb. The gas in each cylinder is now allowed to expand isothermally to the same final volume 2V. That means the gas is allowed to expand isothermally to a volume 2V. Here also the gas is expanded isothermally, volume is expanded isothermally and it becomes 2V. Since it is an isothermal process, so temperature again becomes T, here also it is T. And let M be the molecular mass of the gas. So here if I consider there are N1 moles of gas and if I consider there are N2 moles of gas, so N1 is actually Ma by M and N2 is Mb by M, because both containers contains identical gas, same gas. So if I apply the ideal gas equation P1, before that let us consider the pressure of the gas in container 1 be P1 and that in container 2 be P2. And here the pressure becomes, when it is expanded isothermally, the pressure becomes P1 plus delta P, P1 plus delta P. And here it is P2 plus 1.5 delta P. So P1 TV at the pressure, temperature, volume of the gas and when it is expanded isothermally to a volume V, 2V, then pressure is P1 plus delta P, not delta P1, P1 plus delta P. Volume is 2V and temperature is T. Here initial temperature T, volume V, the mass of the gas contained in the volume is Mb, pressure is P2, it is expanded isothermally, volume becomes 2V, temperature becomes T, temperature remains T because it's an isothermal expansion. That means temperature remains constant during the process and temperature is T and pressure is P2 plus delta P. It is given. Now number of moles present in container A is Ma by M, whereas the number of moles present in container B is Mb by M. Now P1V is equal to N1 RT and P2V is N2 RT. But N1 is what we have written, Ma by M RT, whereas P2V is Mb by M RT. So P1 by Ma, small m, P1 by small ma is equal to RT by Mv, whereas this is one expression. Another is P2 by Mb is equal to RT by Mv, capital Mv. So I can write P1 by Ma is equal to P2 by Mb. This is one expression or one relation. Now, when it is expanded to volume 2V, again I can apply the ideal gas equation, which is P1 plus delta P into 2V is equal to N1 RT. N1 is again Ma by M RT, and P2 plus 1.5 delta P multiplied by 2V is equal to Mb by M RT. So I can write P1 plus delta P by Ma is equal to P1 plus delta P by Ma is equal to RT by 2Mv, and P2 plus 1.5 delta P by Mb is equal to, this is T, this is the RT by 2Mv. So this is one expression, this is another expression. Just simple application of gas law, ideal gas law. So right hand side is same in both cases, so I can write P1 plus delta P by Ma is equal to P2 plus 1.5 delta P by Mb. So I can write from this, so if I just remove from this much, I can remove. So from which I can write P1 by Ma plus delta P by Ma is equal to P2 by Mb plus 1.5 delta P by Mb. But P1 by Ma is equal to, just look at this relation, P1 by Ma is equal to P2 by Mb. So these two we can cancel from either side. And therefore, I can write a delta P also we can cancel, because delta P is not equal to 0. And therefore, 1 by ma is equal to 1.5 by mb. So, or 1.5 ma is equal to mb. Therefore, or 3 ma equal to 2 mb. So this is the correct relation, 3 ma equal to 2 mb. So answer is C. C is the correct option. Simple. P1 by ma plus delta P by ma equal to P2 by mb plus 1.5 delta P by mb, from which we can write 1 by ma equal to 1.5 by mb, therefore 1.5 ma equal to mb, so 3 ma equal to 2 mb is the correct answer. It's a very simple sum, just apply the gas law, PV is equal to nRT. Applying this, we could solve the problem. Very simple. This is solution. This is the answer. I hope it is clear. Okay, let us move to the next problem. What is the problem? A monoatomic ideal gas, initially at temperature T1, is enclosed in a cylinder fitted with a frictionless piston. The gas is allowed to expand adiabatically to a temperature T2 by releasing the piston suddenly. If L1 and L2 are the lengths of the gas column before and after expansion respectively, then T1 by T2 is given by which one of the four expressions ABCD that is to be found out. So before we proceed, let us do a little background work. Consider n moles of a monoatomic ideal gas. Now we are consider that the gas temperature is raised by delta T amount, keeping the volume of the gas constant. V is kept constant. Keeping the volume of the gas constant, the temperature of the gas is increased by delta T amount. Then how much heat energy is required for this process is actually NCV delta T. Very clear, because CV is the molar specific heat of the gas of the monoatomic ideal gas, and delta T is the rise in temperature, N is the number of moles present. Molar specific heat of the gas at constant volume. Alright. Now consider the internal energy, calculate the internal energy of the gas. So it is a monoatomic ideal gas. So for calculation of Q, what we do, half kT is the energy, kinetic energy of single molecule of the gas per degree of freedom. Okay. Kinetic energy per molecule per degree of freedom. Now, since it is a monoatomic gas, degrees of freedom per molecule is, every molecule has 3 degrees of freedom, and in n moles of monoatomic gas, how many molecules are present? N multiplied by Na. Na is the Avogadro number. So this is the total internal energy of the gas, which is depending on temperature only. So U is 3 by 2 N Na multiplied by K T. Here K is Boltzmann constant. Boltzmann constant. You know that. So Na into K is actually R. 3 by 2 N R T. So this is the expression for internal energy of the gas. Now if the temperature of the gas is increased by delta T, then what is the change in internal energy? It is 3 by 2 N R delta T. Change in internal energy is 3 by 2 N R delta T. So it depends on the initial and final temperature basically. So we are considering n moles of a monatomic ideal gas. Its temperature is increased by delta T, keeping the volume constant. So if I apply first law of thermodynamics, dq is dq or delta U plus P delta V. Alright, delta V in our case we are considering the temperature is raised keeping the volume constant. So delta V is 0. Therefore this quantity is 0. So delta Q is equal to delta U. Therefore delta Q we have already calculated NCV delta T. So NCV delta T. CV is the molar specific heat of the gas at constant volume is equal to 3 by 2 N R delta T. So N they cancel from both sides, delta T also they are getting cancelled. So I am finally left with 3 by 2 R. Molar specific heat of monatomic gas at constant volume is 3 by 2 R. Cp minus Cv, you know it is R. Therefore Cp is 5 by 2 R. And gamma, you know, ratio of Cp by Cv is actually 5 by 3. So with this calculation we could find gamma is equal to 5 by 3 for the monatomic gas. So with this background we will go to the problem, actual problem. So gamma we have found 5 by 3. Now a monad Cp by Cv, gamma is equal to Cp by Cv, which is 5 by 3. Now a monatomic ideal gas initially at temperature T1 is enclosed in a cylinder fitted with frictionless piston. So this is a frictionless piston and cylinder at temperature T1 enclosed in a cylinder fitted with a frictionless piston. The gas is allowed to expand adiabatically to temperature T2. Initial volume of the gas be V1, here let it be V2. L1 and L2 are the length of the gas column before and after expansion. So this length is L1 whereas this length is L2. And temperature is here T1 and this is a adiabatic expansion. Adiabatic expansion of the gas. Therefore, delta Q is 0. There is no heat exchange between the gas and its surrounding. Now, alpha, let alpha be the cross section of the cylinder. So V1 is actually alpha L1 and V2 is equal to alpha L2. Okay, this is the ideal gas, monatomic gas. Now let P1 be the pressure of the gas here and P2 be the pressure of the gas here. Okay, so initially the gas is at volume V1, P1 is the pressure, T1 is the temperature, L1 is length of the gas cylinder, gas column, and V1 and L1 are related by this equation. Now the piston is released suddenly and temperature becomes T2, volume becomes V2, P2 is the pressure, and since it is an adiabatic expansion, there is no exchange of heat between system and surrounding. Now, if I apply the ideal gas law, then P1 V1 is equal to, and consider there are n moles of gas. So n moles remain as it is, though temperature, volume, pressure all have changed, but number of moles remain as it is. So P1 V1 equal to n R T1 and P2 V2 n R T2. Alright. Now V1 is actually alpha L1. So P1 alpha P L1 is equal to n R T1 and alpha P2 L2 is equal to n R T2. So what I do, T1 by T2 from these two expressions I can write P1 L1 by P2 L2. I think there is no doubt. T1 by T2 equal to P2 L2. T1 by T2 is equal to P1 L1 by P2 L2. This is one expression. Since the process is adiabatic, so I can also write P1 V1 to the power gamma is equal to P2 V2 to the power gamma. But V1 is alpha L1, V2 is alpha L2, so I can write P1 L1 to the power gamma is equal to P2 L2 to the power gamma. So from this we can write P1 L1 by P2 L2 is L2 by L1 whole to the power gamma minus 1. Okay, so one expression is P1 L1 by P2 L2 is equal to L2 by L1 whole to the power gamma minus 1. Gamma is 5 by 3, therefore gamma minus 1 is 5 by 3 minus 1, it is 2 by 3. So I can write this is 2 by 3. So this is another expression. So connecting these two expressions, this is 1, this is 2. From 1 and 2 we can write T1 by T2 is L2 by L1 whole to the power 2 by 3. So T1 by T2 is given by L2 by L1 whole to the power 2 by 3. So this is correct answer. So D is the correct answer. Very simple problem. We are applying the ideal gas law. This is one. And this expression. These three equations we are applying, and gamma's value we have taken 5 by 3 for ideal monatomic gas, and from which we can find T1 by T2 equal to L2 by L1 equal to 2 by 3. So I hope you have understood. We have considered two MCQs. Past problems is related to isothermal expansion, and this problem is related to adiabatic expansion of gas. So I hope you have understood. If you have any problem, please revert back to us. We will help you further in understanding the problems. So thank you for your listening. Thank you very much.